if we have carbon dioxide, CO2, that means we have one carbon. And the other thing I wanted to point out to you is that I would recommend, when you're showing work for this, writing it out this way, because it will help you find percent composition later. It will make it really straightforward. Okay, I'll accept that one. That's an important thing. Okay. We have one carbon, we have two oxygens, yes? So we look on our periodic table, the molar mass of carbon is 12. And it's not just 12, it is 12.0. Okay, so don't forget that 0.0, because otherwise you're going to lose sig figs later. Okay? Instead of multiplying the oxygen by 2, which I could do, I could say I have 2 times 16, and that gives me 32. Yes? 32.0, because this goes to the 10th position, so that goes to the 10th position. I could actually add them instead. I could say I have one carbon, I have one oxygen, and I have another one oxygen, which would be 12.0, 16.0, and 16.0. And when we're adding, what is the addition rule? Yeah, the addition rule is to go to the first uncertain digit. The other way of looking at that is to the least number of decimal places. In all of these numbers, what is our least number of decimal places? 1 decimal place, right? That is our uncertain digit is in the 10th position. So when we add that up and we get 44, we're going to that 0 there, okay? So it would be incorrect to write your answer as 40, 44. That would be wrong. (44) has only 2 sig figs. We should have 3 sig figs. What else have I forgotten here? Units. What is the unit for molar mass? Well, molar mass, it's actually in the name itself. Part of it is mass and part of it is moles. So it is the grams per mole. And doesn't that make a lovely conversion factor? Right? So that's grams per 1 mole. Alrighty? Now, H2O. The reason I'm bringing up H2O is because if you have a hydrate, it's nice to know the molar mass of water just by heart. You don't have to. Do you remember that example Tyler did that had 7 H2Os in it? And you could add up all your oxygens and all your hydrogens. I think it was manganese, SO4 or something like that, and then .7 H2O. And you remember it was like, okay, we have 1 manganese, we have 1 S, we have 4 O's, and then we have 7 H's, and we have, 14 H's and 7 O's, and then we had to add all those up. Wouldn't it be nice if instead we could say, I have 7 H2Os, and I know that the molar mass of H2O is 18. And then I don't have to go through the whole rigmarole of like adding up all my oxygens and my hydrogens separately. Okay, but either way you do it is fine. Okay. Calcium phosphate, always remember that when you're looking at your elements that are in the brackets, how many phosphorus do we have? 2. And how many oxygen do we have? We have 8. Okay, so is that good? All right. Today we are going to, let me find out where we are here. This is what we're going to do in class today, and then Tyler's going to teach you about converting between grams and moles this weekend. Okay? So we're going to do this with Ms. Spence. And this is 5.1i. It is on page 24. And this is the mole ratio. And I like to refer to this as the particle ratio's big brother. Okay? If you have one nitrogen, or sorry, it shouldn't say nitrogen dioxide, that should say dinitrogen. Tetroxide. Star there, so I fix it. You're going to have 2 N atoms, yes? And that was the ratio that we learned about a couple of days ago. All you do is you go into your atom and you say, how many N atoms do I have in there? Oh, look, it tells me I have 2, okay? So we can say that we have 2 N atoms for every 1 N2O4 molecule, and this ratio here is the particle ratio. Find it by counting within the formula. Super easy. Now we're going to scale this up. So if instead of 1 dinitrogen tetroxide, what if I have a pair? A pair. How many is a pair? 2. So now I have a pair of N2O4 molecules. And I say to you, how many pairs? So I'm doing pairs for both the molecule, and now I want to know pairs of N2 atoms. How many pairs of N2 atoms do we have? We have 2, right? There's 1 pair, 2 pairs. And look, once again, we have that exact same ratio. There are 2 pairs of N, just like there were 2 N atoms. 2 pairs of N atoms per 1 pair of N2O4 molecules, just like there were 2 N atoms for 1 N2O4 molecule. Now we're going to scale up again. What if we drew a dozen N2O4 molecules? How many N2O4s is that? How many is a dozen? 12. So here we have 12. And if we go along and we count our N atoms, there's 2 N atoms, and then 4, 6, 8, 10, 12 in that one line here, right? And in our second line, there are 12 N atoms. So we have 1 dozen, we have 12 of the molecules, 12 molecules. So that's 1 dozen molecules. And we have 12 atoms and 12 N atoms and 12 atoms. N atoms gives us 24 N atoms. So how many dozen N atoms do we have? How many dozen is 24? 2. So we have 2 dozen N atoms. And you'll notice once again, what ratio do we have? We have a ratio of 2 to 1. And now we're going to scale up even further. So I drew out a mole of, no, I did not draw out a mole of molecules for you. I just wrote it down. If you have 1 mole of N2O4 molecules, you will have 2 moles of N atoms in there. It is still a 2 to 1 ratio. That ratio stays the same whether it's a single molecule or whether it is a mole of molecules. Okay? Yes? Nope. Nobody said my name. Okay, I'm imagining things. It's okay. So here we have, we're going to do this with another ratio. In nitrogen dioxide, we have a ratio of 2 N atoms for every 4 O atoms. If we have 2 pairs of N atoms, here's 1 pair of N. And here's the other pair of N atoms. So in total, we have 2 pairs of N atoms. Then we have 1 pair of O atoms, a second pair of O atoms, a third pair of O atoms, and a fourth pair of O atoms. So now we have 4 pairs of O atoms. So 2 pairs to 4 pairs. Does that ratio look familiar? It does. We had a 2 atom to 4 atom ratio. Now we have 2 pairs of atoms to 4 pairs of atoms. Can you imagine what the ratio is going to be for dozens? What if I gave you 2 dozen N atoms? How many dozen O atoms would you have? You would have 4 dozen. So it's 2 dozen to 4 dozen. And you can go count them if you want to. I'm not going to do that. I've done that maybe enough. And then finally, we're absolutely not going to draw them out, but if you have 2 moles of N atoms, how many moles of O atoms do you have? 2 to 4. It's the same ratio over and over again. So if we consider the compound dicarbon hexachloride, so dicarbon means C2, hexachloride means Cl6, we can write a mole ratio of carbon to chlorine where we have a 2 to 6 ratio. So there are 2 moles of carbon atoms for every 6 moles of chloride atoms. We could write a ratio between carbon atoms and C2Cl6 molecules. There are 2 carbon atoms, so 2 moles of carbon atoms for every 1 mole of C2Cl6. So we're doing nothing different than we did 2 days ago. We're just putting the word mole in there for each of them. There are some exercises here. I'm going to let you do them in just a little bit. But before we do that, I'm going to take us through doing a two-step problem using the mole ratio. This is on page 31. And just before we go there, I'm actually going to bop back here and show you, you remember this page we looked at? It's like all the things mole that you could ever need to know. Okay, right now where we are is we are doing this today, okay? And for moles of atoms, you could actually go back and forth between moles of atoms and the number of atoms. What number do we use when we're going between moles of something and individual somethings? Whose number do we use? We use Avogadro's number. So we could go from moles of atoms to number of atoms using 1 mole per 6.02 times 10 to the 23 atoms. This is just on the first page of your workbook. Okay? Let's try a few of these. Let's try the first couple together. And feel free when you're looking at it to use this little thing to help you find your map. Okay? Back on page 31 here. What is our unknown in the question number 1? O atoms. How many O atoms? That is our unknown. So that's where we want to finish. We want to finish with O atoms. And what is our initial quantity? 3 moles of sodium phosphate. So we are starting with the moles of sodium phosphate. Now, if you're given this question and it didn't write it down for you, you would need to say Na has a +1 charge, PO4 has a 3- charge, which means that the formula for sodium phosphate is Na3 PO4. Okay, so we're starting with moles of Na3PO4. We want to finish with O atoms. And whenever I'm changing between one substance and another, there's always going to, moles of one substance to the number of a different substance, there's always going to be 2 steps. So we have 1 step and we have 2 steps. So let's start with our moles of Na3PO4. How many O atoms is equal to 3.000 moles, MOL, remember that's the abbreviation for mole, of Na3PO4. And in this one, we're practicing using the mole ratio. So we're going to go from moles of A to moles of the other substance, moles of A to moles of B. So we want moles of O atoms. We need to cancel moles of Na3PO4, right? Those two are going to cancel out. Where do we get the numbers for moles of O atoms and moles of Na3PO4? We're looking for O atoms. So I look down here and I say, oh, how many O atoms are in Na3PO4? There are 4 O atoms in, oops, I wrote that wrong. There are 4 O atoms in one Na3PO4. So that means there's 4 moles of O atoms in 1 mole of Na3PO4. Is good? Okay. So that's step number 1. We have now found moles of atoms. And when we go from the mole to the number, we use Avogadro's number. Mole to number, we use Avogadro's number. So now we want to cancel moles of O atoms, and we're finding the number of O atoms. What do we use to convert between a mole and a number? Avogadro's number, and that number is what? 6.02 times 10 to the 20? 23, yes. And where do I put that? On the top, 6.02 times 10 to the 23 atoms per 1 mole. And now we are going to plug that into our little calculator. And we get 7.224 times 10 to the 24. Sig figs. We have 4 sig figs here. And we have how many sig figs in the 4 to 1? Those are infinite. And how about in 6.02 times 10 to the 23? 3 sig figs. And how about in this 1 mole? That is infinite. So we want 3 sig figs in our final answer, 7.2. Let's look to the right. That is smaller than 5, so it's 7.22 times 10 to the 24. Am I done? No, what do I have to do? I have to cancel out the mole atoms, and what am I left with? O atoms. And if you are kind to your teacher, what will you do? Box it. Okay? We are now going to try number 3, which is going the other way. My initial quantity is oxygen atoms. So I have the number of oxygen atoms. That's my initial quantity. How many moles of dinitrogen tetroxide? That's my unknown quantity. Is it possible to go directly from O atoms to moles of a different thing? No, there has to be something in between. If you have moles of A, you can find the number of A. If you have number of B, you can find moles of B. But if you have moles of A, you cannot, in one step, go to the number of B. Does that make sense? Okay, so we have to go somewhere in between. There's actually two routes. The one we're going to do here is we are going to take O atoms and we're going to convert it into moles of O atoms. And then we're going to convert that into moles of the other substance using our mole ratio. Is there another route we could take if we wanted to? See if you can chat with your partner. See if there is another in-between step we could do if we wanted to. Anyone got a guess? What could you convert O atoms into? You have the number of O atoms. You could find the number of N2O4 molecules. And from the number of N2O4 molecules, you could go to the moles of N2O4. It's really going to be your choice which direction you choose to go. Which one makes more sense to you? Which one's easier? Maybe, you know, which one makes you feel happier that day? Okay. But either way, it will work. But we're going to follow the blue path today because we have just learned about the mole ratio and we are going to want to use our mole ratio. So let us start with, we want to find the moles of dinitrogen N2 tetroxide O4. And we're starting with 1.204 times 10 to the 24 O atoms. Now here we're wanting to convert into moles of O atoms. So we want to cancel number of O atoms and find moles of O atoms. What numbers go in there? 6.02 times 10 to the 23. Does that go with the mole or does it go with the O atoms? O atoms, 6.02 times 10 to the 23 O atoms for every 1 mole of O atoms. If I know moles of one substance, I can convert it into moles of the other substance. So we have O atoms need to be canceled, moles of O atoms. And we need to find moles of N2O4. And remember, this we just find it from the chemical formula. We take a look and we say, in my chemical formula, I want to find the O atoms, and I have 4 of them in the formula of the molecule. So we have 4 moles of O atoms for every 1 mole of N2O4. .204 times 10 to the 24 divided by 6.02 times 10 to the 23 divided by 4 equals 0.5. Sig figs, 4 sig figs, 3 sig figs, everything else is infinite. So we would need to add how many zeros? 2 zeros. And what's the unit that's left? Moles of N2O4. So these are the things you're allowed to do. You're allowed to go from the number of A particles to the number of B particles and back and forth. Okay, you're allowed to do that. And you do that using the particle ratio. That's allowable. That allows you to go from A to B. You can go from the moles of A particles, moles of A, back and forth to moles of B. And that is, why did I write ratio? I meant ratio. And again, that allows you to go back and forth between A and B. This time you're going back and forth between moles of A and moles of B. And this is what you would use your mole ratio for. You can go back and forth between the number of, oh, this should have been in blue, okay? You can go back and forth between the number of A particles and the moles of A. And that would be using Avogadro's number. But you know what you can't do? You cannot go from the number of A particles in one step to the moles of B. That does not work. You can go from number of B to moles of B. You go from number of A to moles of A, but you can't go from the number of A to the moles of B in one step. You have to take 2 steps. Okay? 2 steps to get from the number of A to the moles of B. Okay? 2 steps. All right, so what I'm going to get you to practice right now do we need this here for a minute? Would anyone like this printed out? Excellent. Okay, I'll make, how many do we want? Hands up high. Everybody. Okay, I'll just print it out for everyone. Okay, So right now, what you're going to do is you are going to, if you're like, I'm feeling a little confused, Ms. Spence, then you can go back to page 26, and that's just practice writing the mole ratio, okay? Pages 26, 27, let me write that down here for you. That's like step one. If you feel like I'm good with that, it's exactly the same as writing the particle ratio, and we did that 2 days ago. I just stick the word mole in it. Then you can skip that. Okay, so that's optional. All right, but if you're doing things later on and you're confused, go back. Okay. You could do you could do page 29 and 30. That would be a good place to start if you're feeling okay with that. And maybe just do every other question, or do it until you feel good about it. And then our final goal is going to be doing these two-step problems on pages 31 through 33. And again, I would say just do every other question. Don't do them all. You'll drive yourself crazy. Okay? But maybe just do every other question. Okie dokie? Give those a try. If you're feeling like you're tired or over and you need to go to drink, that's great. If not, just do a few little stretches until you feel better. Okay? And I will print out that thing for you. There's one. Oh, come here. One. And when you're checking with the answer key, make sure you're writing everything that's there. Or if you don't want to write everything, just ask me, is it necessary to write X, Y, or Z, and I can tell you. Okay? Okay, whatever works for you is the one that you will use. Okay? You don't have to know every pathway. As long as you can get from A to B, it's go. Okay? H is fine. Yep.